Okay, hello. This is going to be chapter 7, which is titled Further Reactions of Haloalkanes. This is where we get into SN1, E1, and E2 reactions. This video is primarily going to focus on SN1 reactions because I feel like SN2, the chapter that we learned earlier, and SN1 has a lot in common. And I think it'll be easier if I do them both in separate videos, E1 and E2. So let's go back to the chapter that we learned, chapter 6, which was reactions of haloalkanes. We learned our first reaction mechanism, which was the SN2 reaction. And we know that it was a bimolecular nucleophilic substitution. This is the general reaction scheme where you have a nucleophile, you have an electrophile, and then a leaving group. And then the leaving group was substituted by the nucleophile, and then the leaving group left. This was the reaction coordinate right here. And we knew that the rate depended on the nucleophile as well as the electrophile. We also denoted that it was one step, despite its name, SN2, it's still a one step. And if there was a chiral carbon, there was an inversion of stereochemistry. Okay, so this is the SN2, simple basics. You needed a good nucleophile, you needed a good electrophile, preferably a primary electrophile or a methyl electrophile, and then you needed a good leaving group, which was a weak base, right? Denoted here. So now we're going to get into SN1. And if SN2 was bimolecular, then SN1 by the name is unimolecular, right? So instead of depending on um, two substances. Oh, the rate here is given by the nucleophile and the electrophile, right? So instead of relying on two molecules, you're actually only relying on one, which is only the rate of the electrophile. So let's see why this is important coming up. This is the general reaction scheme. You form a positive nucleophile here, and then there is something different here. As you can see, there is a transition state denoted by this electrophile with a positive charge. It's usually two major steps. You can argue that it's three. I usually think of it as two major steps, and it, unlike SN2, it does involve an intermediate, and this is going to be the most important thing about SN1 reactions, okay? So because the reaction only relies on the electrophile, we don't really need a good nucleophile. We can have a semi-good or even a bad nucleophile is okay because it's all going to depend on the electrophile, okay? So let's see why it depends on the electrophile. I have an example of a reaction right here. As you can see, we have methanol, right? H3C with an OH. We have this bromine and then this carbon here. This is going to be our nucleophile right here, and this is going to be our electrophile leaving group. And then you get the same compound, which you would in a substitution reaction, and you get an HBr at the end. Okay, so let's see why this happens. You can see here that we have a bad nucleophile, right here. And then we also have a tertiary electrophile, right? This carbon is attached to 1, 2, 3 carbons over here. So this is a lot different than SN2. In fact, I think it's the exact opposite. It looks like it's the exact opposite, right? Okay, so let's see what goes on. This occurs in two steps. Like I said, there's two major steps. So let's see the first step. The first step is the leaving group, denoted here, is actually going to leave, okay? Now, if the leaving group leaves, so let's say I'm going to draw this in a Lewis structure so it's easier to see here. Sorry for not drawing the wedges or dashes. So if the leaving group leaves, it takes both its electrons, right? Remember, covalent bonds are shared electrons, right? If I draw an arrow from the bond to the Br, that means that the carbon lost its bonds, right? So let's do a quick formal charge. Formal charge is the valence electrons minus the bonds, and then minus electrons that it has, right? So here I see carbon is a 4. It has three bonds connected to it, right? 1, 2, 3. So 3. And then it has no lone pairs of electrons, so 0. So this makes it a positive 1. So here we have a positive carbon. And there is a special name for this. It's called a carbocation, right? So carbon and then a cation. So it's a carbocation, right? And we'll get into this later, but this is the major key to an SN1 reaction. You have a carbocation intermediate, right? The intermediate is the thing that we saw here, the transition state. The intermediate, sorry, this isn't transition state, this is intermediate. Intermediate. So we do have that intermediate, and that's part of our reaction coordinate system, okay? So now, as you can see here, we have now two nucleophiles, two possible nucleophiles that we can react it with, right? We can either react it with the bromine, or we can react it with the methanol, right? So what would happen if we reacted with the bromine? If we reacted it with the bromine, we would just go back to our reactants, right? We have the bromine here, it just left. So if we attack it again, this is going to become this other compound, right? So we don't want that. We usually want the reaction to go forward instead of backward, right? So instead, we're going to react it with the methanol. And actually, the methanol is sometimes when we do these in reactions, we tend to have the methanol in excess. So that just means the bromine will just slowly drift away into your beaker, but you'll have a lot of methanol left, so it's able to react with the carbon. And it's able to react with the carbon. We said that the OH is a bad nucleophile, right? But it doesn't matter because now we have a fully positive carbon. It doesn't need a strong nucleophile. Remember, strong nucleophiles were usually negative charges. The reason why it was a negative charge is, the reason why we needed a negative charge in an SN2 reaction is you usually had this dipole moment, right? Where it was a partial positive and a partial negative. If we react it with this, it's only a partial positive, which in an SN2, it won't occur. But now since it's SN1, you can get away with having a weaker nucleophile because now the rate only depends on our electrophile, which has a fully positive carbon, okay? So step 2 is the nucleophile will attack the carbon, okay? And then if it attacks the carbon, you form this compound right here, this positive hydrogen, because we did a formal charge, right? So oxygen has a valence of 6. It has 3 bonds connected to it, right? And it has 2 electrons, okay? So that is 6 minus 5, so that's a positive 1. And what do we know about oxygen? Oxygen is a not very, but it is an electronegative element. So if it's an electronegative element, it doesn't want this positive charge, right? It either wants to be neutral or it wants to have a negative. So having this positive charge on an oxygen is actually really, really bad. But we also have something else here, the leaving group that just left, right? From this reaction, the leaving group left first right here. So we still have this in the solution. So there is a acidic bond here, if you see it, and we also have a base. So the acidic bond, like I said, in a C to Br is a dipole here, right? So this is a delta negative and this is a delta positive, which means C is delta positive, which means a nucleophile can react to it, right? So in this case, we still have a dipole moment here. We have the oxygen, which is a delta negative, and we have the hydrogen, which is a delta positive. If we have a delta positive and we have a bromine, we can just react it with the H. So the bonds from the O to H can go straight to the oxygen, which can get its electrons back. So what happens if we do that? We attack the hydrogen here. The O to H bond, both electrons go to the oxygen, making it now an ether, but now this is, right, the two electrons that were shared in this bond goes straight to oxygen, and now the Br attaches itself to the hydrogen. This is an acid-base reaction that you learned in chapter 1 or chapter 2, I'm not too sure. So now, if we do a quick formal charge on this oxygen, it has 6 valence, it has 2 bonds, and then now it has 1, 2, 3, 4 electrons. And this is 0, so it's neutral, so it's good. Okay? So let's go through again what we did. The first step of an SN1 reaction, the leaving group left. The leaving group left, which forms a carbocation intermediate, a carbon with a cation, right? It can react with the bromine, it can, but if we react it with the bromine, it's just going to go uh, back to our starting material here, and that's what we don't want, right? So then, since we have a fully positive carbon and we have a weak nucleophile, we can still react it with the carbon because it is fully positive, right? Compared to an SN2 where you need a really strong nucleophile. In this case, you don't. So once that happens, you form this intermediate where our nucleophile was positively charged and it has an acidic H bond here that the bromine, a base, can grab, making it a stabilized ether right here. Okay? Okay, so that was a lot. I understand. So take a few moments to fully understand this concept of two steps. Um, so we're going to go into carbocation and what makes a carbocation stable. Okay, so something called hyperconjugation. You've learned this. If you read the book, it was discussed in around chapter 1. And you are actually also saw this with radical halogenation, right? With radical halogenation, we figured out that a tertiary radical is better than a primary radical, right? Because I'm actually going to draw the radical here because of the hyperconjugation. So what does hyperconjugation mean? It I don't like using this word basically, but it simply means neighboring CH groups, neighboring methyl groups, or substituents donate their electron density to stabilize the carbocation. So this is the same thing as the carbocation or radical. In this case, we're going to focus on the carbocation, but think of it similar to a radical. It has all the same it doesn't have the same chemical properties, but it has the same properties to make it stable as a radical. So in this case, look at this carbon here that's attached to the bromine. It's attached to 1, 2, 3. So it's a tertiary carbon, right? If it's a tertiary carbon, we form a tertiary carbocation, right? Oh, this is supposed to be a CH3 right here, CH3. Now, if it's a tertiary carbocation, it has this methyl group grabbing this positive charge, donating its electron density to this carbon. It has another one stabilizing it even more. And it also has this third one, which stabilizes this even more. So even though this reaction doesn't look favorable, this formation doesn't look favorable, it's helped by the stabilization of hyperconjugation. These neighboring methyl groups donate their electron density to this carbon, making this positive a bit more easier to handle for this carbon, which stabilizes it, okay? So once we have that, let's take a look at how these electrophiles or how these carbocations are ranked, okay? So I told you tertiary is better than secondary. We have the same nucleophile here in ethanol, but we have a tertiary carbon, secondary carbon, primary carbon, and this primary carbon, okay? So out of these four, which one is the least stable? If you said the third one was the least stable, you are correct. This is the least stable. And why? It's because it is a primary carbon as opposed to these other secondary and tertiary carbons, which means it's the less stabilized, right? So now, which one is the most stable? If you said that the most stable one was the bottom, you are correct. So let's see why. I know the top one may look may look really stunning because it is a tertiary carbon compared to a secondary carbon, but there is a little something here that's going on. We have a positive charge here, right? If this chlorine left, we form a positive carbocation, right? You're gonna see me use that word a lot in this lecture or in this video. Um, but there is a double bond in close proximity to it. So you did this before, and this will come up again and again and again in 40B and 40C, the idea of resonance. So this double bond can come here, right? Making it a resonance stabilized structure, which in the world of carbocations and in general in the world of chemistry, so now the positive charge would go here, a resonance stabilized form is a lot better than hyperconjugation. But why? It's because now instead of partial donation of electron density, you actually get full donation of electron density here, right? This positive charge is evenly split between this carbon, and this bottom carbon. So it's evenly split. That's why it's the most stable. But in this case, the carbon is only stabilized by these neighboring methyl groups, but it's staying on this carbon, which means it's staying on that carbon, meaning that it's only stabilized by hyperconjugation. Yes, this is stable, but when you compare it to a resonance stabilized form, it's least stable. So this would be our most stable because of resonance. And then, as you guessed it, this would be our second most stable. And then this would be our third because it's a secondary carbon, okay? So let's do an example of what we have here. So this example right here, okay? This OH plus this Br. So what was the first step of an SN1 reaction? The leaving group leaves. So the leaving group leaves, and then we form a carbocation, right? We form a carbocation right here. And then we have the bromine, which just left, right? Boom. And then we can attack the carbocation with our weakly methanol because it's a carbocation, right? Boom, right there. Easy peasy. OH. Oh, let's draw this full molecule. Right, the O attacks, so it's going to be attached to the O as an H right here, and it has the methyl group sticking out. Plus, we have a bromine still. Okay. And then now this oxygen is, let's do a quick formal charge. Valence is 6. It has 3 bonds and it has 2 electrons. So it's a positive. But we have an acidic hydrogen right there on top of the O. We can just grab it. This one goes there. And we get the top product right there, which is this. HBr, right? But it's not really the case, and it's not what we see here. The actual product of this is actually down here instead of up here. So let's see why. Remember how I said tertiary carbocation is better than secondary and is better than primary? Look at this carbocation right here. it's a secondary carbocation. But what if there was a tertiary carbocation right below it, which there is right here, right? If they, let's say the positive charge was on this carbon, it would be a lot better, right? Because it's 1, 2, 3. And this is what we're actually going to see happen is this whole process isn't going to work. It's not going to be favored. Rather, you see something called a hydride shift, right? The positive was right there. So let's draw this molecule out, C to C, bottom C, C, C. Let's draw in our hydrogens. This is, it only has one more hydrogen, so this is a positive carbo. I'm going to draw that in a different color so it's easier to see. And then we have one H here, and then we have 3. Okay, so what actually happens is neighboring carbons, so these two, can donate one of the hydrogens to this carbon, shifting this positive charge to either this carbon or this carbon. Okay, so we can't take it from up here, because if we put this hydrogen here, this would make a primary carbocation, which is a lot worse than what we have now, right? But we can take the hydrogen from here, which is a tertiary carbon, okay? So let's see how that works. So then it's a simple mechanism. This hydrogen bond is going to go to the H, to the C, and then we're going to form. So now this carbon, which was missing a bond, now has the H, and then this carbon right here, let me draw in my H's real quick. So this carbon once had the hydrogen, but the hydrogen shifted to this carbon. Now this carbon has the hydrogen. So where did this positive charge go? The positive charge went to this carbon right here. And now, is that a lot better than a secondary carbocation? It is, because now it's a tertiary carbocation. So that's actually what happens in this step. So we have this positive, right? There's a implicit hydrogen right here, which can, actually I'm gonna make this a bit bigger. Does it look like that? Oh, and then like that. So the hydrogen was up here. We had this implicit hydrogen right here, and then it transferred over to this carbon, and then now we have a tertiary, a tertiary carbocation right here. And then now we can do the exact same step again with this methanol to achieve this compound right here. And this is plus HBr. Okay? So this is called a hydride shift. And it's one of carbocation rearrangements. So again, we have the carbocation shift. I denoted that here with this golden H, right? If there is a better carbocation available, right? This is a tertiary carbocation compared with a secondary carbocation, the hydrogen will actually shift over, making it a tertiary carbocation, which is much favored, right? I denoted that with the golden H here. That's called a hydride shift, hydrogen. Or there's called an alkyl shift, when you move a whole alkyl group over, right? I denoted that with this. Again, if there is a possibility of a better tertiary, or if there's a possibility of a better carbocation, right? Or there's something called a ring shift, which happens right here. So what actually happens is this bond from the ring will actually move up here, So how do we denote that if this bond from the ring moves up here? Let's number the carbons. 1, 2, 3, 4, 5. And then we see that the 5 carbon bonded with the 1. So the C to C, this bond moved up here, right? So what actually happens is, the easier way to do this is we draw a pentane ring, because it's 5, right? Oops. And we number it 1, 2, 3, 4, 5. At the 1, there is a positive, there's a methyl sticking out. Where did the positive charge go? This bond from 5 to 2 went up to 5 to 1. So then the 2 now has the positive charge, which is going to be denoted here, right? But there is also something else going on here. Like I said, there is a hydride shift down there because this is a secondary, and now if it goes up here, it's going to be on the tertiary, right? So it's going to be up here now. Okay, so that's called a ring shift. This rarely occurs. A ring shift rarely occurs, but it does occur, and it's not going, you might get tested on it, but I would just worry about a hydride shift, okay? So the moral of the story here is, whenever you form a carbocation, always, always look to the left and to the right and up and down from it to see if there are any places that it can be stabilized even further. So for example, we have this, right? Let's look to the right. There's nothing to the right. There's nothing above it. There's nothing below it, but there is something beside it. And is this going to be a better place for the carbocation? It is, because this is a tertiary carbocation as opposed to a primary, which means it will be better at holding the positive charge. So there is going to be a shift here, right? That's a lot better than a primary carbocation, okay? So whenever you come across a carbocation, whenever you form a carbocation, always look one bond ahead, okay? Ahead, behind, up front, whatever. You always look one bond ahead to get this correct, because this is a very important formation. And this is actually also why SN1 reactions only matter with the concentration of the electrophile, because the carbocation drives this reaction. Okay, so this was SN1 in a nutshell. I hope that it was able to help you all, and I will be making an E1 and E2 coming up next. And I hope you all have a good day and good luck on your midterms. Okay, hello. When I went through the video and I edited it, there was something really big that I missed about SN1 reactions, and I truly apologize for that. This is a very minor thing, but I think it's very important in your understanding of um, organic chemistry. So I forgot about our good friend stereochemistry. So let's take a look at this reaction right here. This is an SN1 reaction, right? The leaving we have a chiral carbon right here, right? We have 1, 2, 3, 4 different distinct substituents. If this bond leaves, we get this this intermediate, right? This carbocation intermediate. So because we have this carbocation intermediate, there is a possibility that this oxygen will attack from the front side, or it can attack from the back side. So we chemists don't really know or can see this happen in a lab setting, but we know from theory that it can attack the front side or the back side because now there's nothing hindering it, right? Remember in an SN2, we always attack the back side because we had all those orbitals that were hindering it, but now we have an empty orbital right here because of this positive charge, which means we can attack it from the front side or the back side, right? And because we can attack it from the front side or the back side, we can flip the stereochemistry again. So we form these two groups. The only difference here, this H is on a dash versus this H is on a wedge, depending if we attacked it from the front or the back, right? This is our deprotonation process where we take the H and then we have the O. So let's go to our finished product here. So we then would have these two different molecules where this H again is on a wedge, on a dash, and then this H is on a wedge, right? So let's do our R and S naming. So we're focusing on this carbon. This oxygen is number 1. This group would be number 2. This one would be 3. The H is on the back and it's the 4th, which is good. This is an R because it goes clockwise. So if that H is on the back and it's an R, this H is now on the front. So we should flip it. So it's S, but let's just make sure that's truly the case. This is 1 over here, 2, 3. We're going clockwise, and this 4. But our 4 isn't on a dash, it's on a wedge, so we can just flip it. So it's S. And now because we have these two molecules, it's not going to be 60-40 or it's not going to be 70-30. Not one of these molecules is going to majorly be produced. They're going to be produced in a 50-50 ratio, right? So you have 50% that is R, and you have 50% that is S, okay? So let's think about it in a physical type of way. Let's say we know chiral molecules, they can rotate light, right? They can rotate light. So let's say our R rotates light in the right direction. So R rotates light right. Okay. And then let's say S rotates light left. Okay. If we just have 100% of R, it would rotate it to the right. If we would have 100% of S, it'll rotate it to the left, okay? But what happens if we have a 50-50 mixture of R and S like we do in an SN1 reaction? If we have a 50-50 mixture, that means it's gonna 50-50 rotate light to the right, rotate light to the right, and 50-50 rotate light to the left. So what happens is it actually cancels out right here. So that means these mixtures, these 50-50 mixtures, 50 mixtures can't rotate light anymore. Can't rotate light. And these are called racemic mixtures. Okay? And because they are 50-50, because they occur in both R and S 50-50, that means it's racemic, which means it's going to be achiral. Okay? Because it's a racemic mixture, it can't rotate light anymore. So even though it has a chiral center, if it can't rotate light, then it's not chiral. So it's achiral. And we call this racemic mixtures. So SN1 produces racemic mixtures if chiral carbon. Okay, so I hope that this is I hope that this helps. Even though it's chiral, it doesn't have any way of rotating light because it's 50-50 and it's going to go in opposite directions. So yeah. So again, SN1 reactions, they occur in two steps instead of one. They have a carbocation intermediate, which is stabilized by either hyperconjugation or resonance. And tertiary carbocations are better, which means hydride shifts and alkyl shifts can occur. And if you have a chiral carbon attached to your leaving group, it can either attack it from the front or the back, which means you're going to create um, two mixtures that are 50-50 present, which are called racemic mixtures, and they are not chiral. They are achiral. Okay. So again, I'm sorry if this for being out of order, but I hope this was able to help.